Hello everyone, my name is Jonathan Hanna, and this is my presentation for the final project for the PHYS1060-A photographing physics class with Professor Buxton. So, we'll start things off. I've learned a lot about this show, I've learned a lot from this class, whether it be about photographs, physics, just a whole bunch of stuff this class has helped teach me, but let's get on to it. So starting in week 1, the themes were color and the rule of thirds. So I have a picture from RMU men's soccer as they took on Bryant. This was a couple months ago now, near the start of the year, obviously. And what I noticed is I used the rule of thirds here horizontally. I know a lot of people use it vertically, but there's definitely 3 distinct areas of this photo. In roughly thirds, there's the field, the trees, and the sky. And for color, the sky is definitely blue, and this is due to the fact that blue has the shortest wavelength, and the shortness of those blue waves allows it to be spread by the ozone the most. Now, going on to week 2, this is a picture of the U.S. Olympic Committee headquarters in Colorado Springs. You're going to notice a lot of pictures from Colorado Springs. I went there on vacation over the summer, and there were just some great photos. So, this week's theme was symmetry and reflections. And as you can see in the building, it's very symmetrical. If it wasn't for the blinds in the windows and the lettering on top saying United States Olympic Committee, this building would practically be symmetrical on both sides. Same number of windows, and then the 2 pillars down at the bottom are really separating that. And then for reflection, the clouds on the bottom few windows are being reflected by, obviously, those windows. And this is really due to the law of reflection, which states that if an angle from the sun, it bounces back the image in its reflection. For week 3, the theme was physics. And what I did was just a really simple picture of a straw in a glass of water, but you really saw the refraction here. And the quick reason why water isn't a liquid, or is the liquid in this state, is because it hasn't reached its boiling point of 212 degrees Fahrenheit, 100 degrees Celsius. And it hasn't reached its solidifying point where it becomes ice at 32 degrees Fahrenheit or 0 degrees Celsius. And the big reason this change that happens in the straw, obviously it's thin above water and quite thick and a bit off-kilter below the water, is due to the fact that the light that's shining is going through a different medium, and the water is more dense than the surrounding air. So going on to week 4, this is a picture of the Garden of the Gods. I mentioned a lot of them were in Colorado. It's a really nice little natural wonder. I don't think it's actually considered that, but it's just outside Denver. Lots of red sandstone, a lot of nice pine trees, and a lot of blue sky. And the sandstone, the theme was shadows and really just framing for this one, and the red sandstone framed the picture, giving the viewer a terrific glimpse at solely the pine trees and the blue sky in the background, and also the red sandstone and the sky really contrast with each other. And for shadows, they're a lot shorter in this picture than they would be if I took it at a different time. I took this around 2:30, I think, and the sun was directly overhead, meaning the shadows would be short. But if I took the picture at early in the morning or later at night, the shadows would be a lot longer, cascading over the red sandstone rocks. Now, the final picture in Colorado, I promise. It's a picture of Clear Creek in Golden, facing Mount Zion. You should be able to see on the mountain there's a M that's just made out of small little white rocks, and it's referencing the Colorado School of Mines, which is in Golden. And this week's theme was depth and leading lines. So the depth in this picture is shown because the further in the picture you go, the trees get smaller, giving that sense of depth in the background that this picture just keeps going and going. And for the leading line, you can really see this river acting as the reading line, sort of paving a path through the middle of the photo, making that left-hand curve out in the distance, making you really look at that river and following the river as well. For week 6, it was macro photography, and this was really my favorite picture that I took. It's a picture of a rivet from a foundry skeleton in Lawrenceville, PA. So one thing about this rivet is that there's a lot of rust, or also known as iron oxide, Fe2O3. And it's caused by iron surface, in this case the rivet obviously, being exposed to the elements, so your wind, your rain, your snow, your hail, stuff like that. And what it does, it loosens the structural integrity of the iron itself, and it also flakes the paint. But the rivet, in this case, is a great example of physics because it's able to do a job as well as it is because of physics, pretty much. So what happens is they're heated really warm, put into a hole, and then hammered on the other side while it's still hot, obviously, so the iron is malleable. And as the rivet ends up cooling, it ends up expanding within the structure and causing friction between the joints of the structure. For week 7, it was a free-for-all, and it was a picture of warm-ups that I took between the RMU women's hockey team and the number 2 ranked Minnesota Golden Gophers. And for my my physics, in this picture, even though it's not shown, I really tried to focus on the physics of a slap shot, which, if done correctly, can be one of the most lethal shots in the game. Actually, the hardest slap shot was done by a Bruins defenseman in NHL history named Zdeno Chara at the All-Star Skills Competition. In 2012, he shot at 108.8. But how the physics in this happen is it's focused. So it's the transfer of weight from a player's back foot to their front foot during the slap shot and the follow-through, and concurrently the energy from that weight transfer to the blade of their stick to the puck, and hopefully for that player to the back of the net. And finally, I decided to do one that sort of describes me. I did a picture of some garlic Romano wings from Vocelli's, which is a nice little place down the street. See, this describes me because I'm from, pretty much Buffalo. I'm from Rochester, New York, so wings play a big part in my childhood and what I like to eat. And I really didn't see many food physics-related pictures on blackboards, so I figured this would be a good one. So when foods are fried, like wings often are, it's done in hot oil, so 350 to 375. That's obviously higher than the boiling point of water, but oil obviously has a higher boiling point. But so the surface would dehydrate the wings, giving them a nice crispiness. But once the surface dehydrates, it sort of creates an impermeable surface for oil. So heat can continue to get inside of the food, but oil is not allowed in. And funnily enough, the University of Leicester in the UK found out that for a normal-sized buffalo, if it actually did have wings, they need to have an area about a third of a meter squared. So that's a third of a meter on all sides to create enough lift for the buffalo to take off when having a running start at maximum speed. So while that size doesn't really make much sense, it's about 30 times the size of a normal wing. So you'd have to have either 30 small wings or one giant wing. Obviously 30 times. But that's all from my presentation. I hope you enjoyed it, and I really learned a lot from this class.